Thank you so much for having me here. It is really exciting and a great pleasure to get to talk to everybody about one of my absolutely favorite subjects, asteroids. I really was excited to find the font that goes with the old video game. As I was telling Todd, I spent way too much of my childhood playing this game, much to my family's consternation. I used to just love to come home and blow away a bunch of asteroids. Well, as it turns out, this wasn't entirely wasted effort. The game is actually pretty realistic. There are a few big pieces. If they are hit with something, they break into a lot more small pieces. And there are many more small pieces that are zipping all around than there are the big pieces. So from that standpoint, this was research. It was an okay thing to do. That's my story, and I'm sticking to it. So let's go ahead and get started. And I'll tell you a little bit about more what we know, what we don't know, and what we're going to try to do to find out about it. So just starting with some events of recent memory. So that sort of begs a few questions. The first one is, how often does this happen? And what is being done about it? The pops that you heard as the event sort of rumbled on, that was actually an asteroid breaking up in the atmosphere, and each noise you hear is a piece of it breaking apart. So we'll talk a little more about this particular object in a bit, but first I'd like to just kind of go over some basics about asteroids. We have a lot of jargon in this field, and there are three things here, three terms that are commonly thrown about. Yeah? Oh, okay, yes. Oh, is that better? Great, okay. Thank you for pointing that out. No, thanks for pointing that out. That's good. We want you to be able to see it. So there are three terms: asteroids, meteors, and meteorites. These are all terms that refer to the same thing. It's a rock. One is a rock in space. We call it an asteroid if it's sort of a free-ranging rock that's floating around in space. We call it a meteor if that same rock were to enter the Earth's atmosphere. And if enough of it survives passage through the atmosphere to make it to the ground, we now call the rock a meteorite. Same thing, three different terms. Just the terminology distinguishes what's happened to the rock as it's made its journey through the solar system to the Earth. Okay, so the question is, how do asteroids get here? Well, to answer that, we need to begin at the beginning. So going back to the formation of our solar system about 4.5 billion years ago, things started off with a giant revolving cloud of gas and dust that slowly collapsed under the influence of gravity. As it did, you can start to see this swirling disk form with condensations in it. These are the protoplanets. Eventually, as gravity attracted more and more material, just like a snowball rolling down a hill, getting bigger and bigger and bigger, most of the material in the dust is getting swept up into either our sun in the middle of the cloud or into the planets. But as you go forward in time, you can start to see there's a little bit left over. Not everything made it into a planet. The planets did not sweep up all the material, all the bits and pieces. So because of this, that's why we have asteroids. Asteroids and comets are sort of the leftover fragments that didn't get swept up by a planet or some other large moon or other structure, or the sun. So the solar system, as it turns out, is a pretty busy place. This is a sort of a map, if you will, of where the asteroids and comets are in our solar system. And so just to kind of give you the sort of top-level view, here we have the the orbit of Jupiter, right here. This is the outermost circle. And it's a little hard to see, but there's Jupiter slowly going around the sun. And you'll notice there are a couple of dim blue blobs that sort of lead and trail Jupiter. These are clouds of asteroids that are gravitationally trapped by Jupiter. Going back to my Greek mythological roots a little bit, they're called the Trojan Asteroids. And there's a leading cloud and a trailing cloud, so we'll hear a little bit more about those. Jupiter's gravity is so powerful that it keeps these asteroids shepherded in place as it goes around the sun, and these clouds stay with it, and they share Jupiter's orbit. Going inward, we have a huge, vast swarm of asteroids that mostly sit here perfectly harmlessly between Mars and Jupiter, and this is what we call the main asteroid belt. And most of the material in the inner solar system, in the small bodies, is here among the main belt asteroids. We know of hundreds of thousands of them today, and for the most part, they just stay there, harmlessly circling the sun, but a few things can happen to them. They don't all always stay there. Some of them actually can get a little too close to Jupiter or one of the other planets and get into a resonance. They can be scattered out of the solar system. Sometimes they can actually get pulled into the sun, and other times they can hit a planet. Now you'll notice it's a little hard to see, but there are some dim red dots in there, in the inside, the inner planets. These are called the near-Earth objects, and this is the population that isn't always staying harmlessly out of the way of our planet. These are asteroids and comets that get relatively close to the Earth's orbit around the sun. And this is a population that we'd like to know more about because we'd like to know how often impacts like the one in Russia occur. As of today, we know of about 16,000 of these near-Earth objects, but as we'll see, this is thought to be only a very small fraction of what is actually out there. So the next question is, well, how big are these objects? Well, just for scale, here is our moon, and this is the largest asteroid in the asteroid belt. This is also known as a dwarf planet. It's called Ceres. And then we have Vesta right next to it, and both of these objects now have been visited by spacecraft. The Dawn mission has actually been to now both of these large bodies and has delivered these amazing, beautiful maps. But it gives you an idea. That's the biggest asteroid, and about a quarter of the mass of the entire asteroid belt is contained just within this one object right here. So for scale, here is Vesta that you just saw in the lower left corner, now shown with the few asteroids that we've actually been to with spacecraft, either a visit where we actually orbit around it or we flew by it on the way to something else. And all the way down here at the bottom is an asteroid called Ichikawa. This was visited by the Japanese Hayabusa mission, which actually brought back a very precious small sample from it. It's so small it doesn't even show up as a dot on this image, yet this object is about half a kilometer across. So that gives you a sense of scale. We're starting to see just how big even a small asteroid really is. Okay, so I always like to show this, myths and misconceptions. I love Star Wars, I'm a huge sci-fi fan, but this isn't right. When they fly through the asteroid belt, this is what it would really look like if you were actually flying through the asteroid belt. A lot more boring looking. Basically, even as big as these asteroids are, they are so far apart that seen from the surface of an asteroid, the next nearest one would most likely look like a star, like a dot. So that's a common misconception, although I think for artistic license, a lot of times we try to make it more exciting in the movies. And shooting stars. This is another one of my favorites. On average, most of the shooting stars you see are just the size of a sand grain. They're tiny, tiny little things. So how is it that they can be so incredibly bright? Well, a very bright one might be as big as, say, a rice grain or even a pea. But the answer is it's a pea traveling at 20 kilometers per second. That's about 40,000 miles an hour. So even a tiny little piece of sand or a grain of rice traveling at that incredible velocity packs the equivalent punch of multiple sticks of dynamite. And that's why it's so bright. All of that mass is getting converted, or a large fraction of that mass is getting converted into energy that you can see in the form of light and heat. So what are these near-Earth objects that we were talking about? Well, they come in kind of two varieties, the cometary bunch and the asteroidal bunch. And broadly speaking, you could think of these as two ends of a spectrum. Comets tend to have a lot of ices trapped within them, and so there's sort of dirty snowballs is one way to think of them, or even snowy dirt balls. Basically, it's a mixture of various types of ices and rock and clays, all in a nicely packed mix. And as they get close to the sun, those clays and ices start to evaporate or actually sublimate, convert directly from solid to gas. And that's why we see these tails and beautiful jets coming off of comets. On the other end of the spectrum, you have the objects that are not as volatile rich. They don't have the ices to the same degree. And these are asteroids. This is what we call them. Basically, they're rocks, essentially, but they're broken up, they're shattered. They've sometimes been produced by multiple collisions with one another. And there's quite a variety of them. Just like rocks on Earth, there's an enormous diversity amongst the asteroids and comets. Some are very, very wimpy kind of comets that lost their ice, and they're sort of crumbly and very weak. And some of the asteroids are more like lumps of solid iron, practically. So there's quite a range of types and classes. We have a lot of evidence that impacts from these bodies have happened on Earth, but the question is how often and when does it happen? So from the Tunguska airburst of 1908, this was probably roughly a 50-meter object that exploded over Russia. Poor Russia, they keep getting these asteroids. But it's the size of the landmass. I think that's responsible there. It's just a coincidence. And then we have this crater right here that was beautifully imaged from the International Space Station. This is about a 1-kilometer crater right here. Some of them, however, are much larger. And even though it looks the same size roughly on the screen, this one in Canada is about 100 kilometers across. The impactor that made that was the size of a small mountain, about 5 kilometers. Of course, the big one of all that everybody is probably most familiar with is this one in the Gulf of Mexico. This is about 200 kilometers across, and this is actually an image of it. It hit in the Yucatan Peninsula in Mexico about 65 million years ago. This is an image of the crater, one piece of it. And basically, there are signs all over the Earth of this impact having happened. There are all kinds of rare earth elements and minerals that are just found that are really only produced when a very high heat suddenly happens to rocks, producing fused glass and bringing elements such as iridium to the Earth, which are not really super common here. And we see this all over the world in different places. And this one part of the fossil record. So the impactor was thought to have been 5 to 10 kilometers across, very large, and basically it would have been like the entire world's nuclear arsenal and then some going off all at once. It was really, really bad. And basically what happened at the time is there was an enormous blast wave, flaming debris probably rained down on the Earth in a pattern similar to this, and it created forest fires on a massive scale. So one of the things that researchers are studying is what were the impacts of releasing all that carbon dioxide in one sudden big pulse. Everybody thinks about the debris screening the sun, which probably temporarily cooled the Earth, but suddenly releasing a whole lot of carbon dioxide could very well have created a huge sudden spike in carbon dioxide levels. So in a sense, we have done the experiment with suddenly raising the CO2 levels, and the result was not great. I would recommend that we don't do that again. So there's a lot to be learned about this with our present-day situation. This impact, of course, was thought to have given rise to the mammals, including ourselves. It really did wipe out a good fraction of life on Earth, both on land and in the water. And mostly the really big animals didn't make it because the food chain collapsed. And you can see here a plot that basically is in hundreds of millions of years before present. And these are the sort of major extinction events that happened. And this is what happened by looking at the number of genera. So you have species and genera, which are the groupings of and diversity of life on the planet. It really took a pretty whopping hit. And it did come back and reached even greater levels of diversity after that, but it took a few million years. So you can see that life on this planet can sometimes recover and bounce back, but it takes a very long time on any sort of human timescale. So we'd like to keep things good here. So to come back to that object that we saw in the beginning, now let's talk a little bit about that. Now we know how big the biggest asteroids are and how the smallest ones can even be quite bright. This particular object was only about 17 meters across, so that's roughly the size of this auditorium. It was small. That was a very, very small asteroid, and that's what it did. It was roughly equivalent to 11,000 tons, and many pieces of it were actually recovered, which makes it a really remarkable find because it lets us study what these things are actually made of. I have a piece of it here. This is actually my own little fragment that I was able to get thanks to a colleague of mine. And you can see some really interesting things about it. First of all, the outside is burned. That's because of traveling through the atmosphere at about 40,000 miles an hour. That'll do it to you. The inside is riddled with these little cracks. And we think that this is basically evidence of previous impacts that the object suffered a long time ago, over tens and hundreds of millions of years. This is evidence that this poor object has really been through the mill. So anyway, that tells us a little bit more about these objects and what their nature is, but it still doesn't completely address the question of how often does it happen, and what do we do about it? So one of the more famous impacts that really spurred people to think, in spite of all the craters that we had seen, a lot of times there was a sort of a sense that, well, this happens on geological timescales, but not on human timescales, so it's really not worth paying much attention to. Well, this event really did get everybody's attention, I think it's safe to say. And this was a comet that was discovered before it was found that it was going to impact Jupiter. Jupiter tore it into pieces. Jupiter's enormous gravity actually shredded the comet, and astronomers were not sure what would happen when the comet impacted Jupiter. Some people, I believe, thought that Jupiter would just swallow it up. Other people thought it would leave a detectable signature. Astronomers all around the world observed it. It is a really magnificent campaign that was carried out. And here is the image from a series of images from Hubble, culminating in this one right here. So here's the great red spot. Each one of these scars is roughly the size of our planet. So yeah, impacts can happen, and they can cause detectable effects. So how often? That's the key question. We know that really big impacts, like the one that wiped out the dinosaurs, must be very rare, or we would not be here. So those happen on sort of 100 million year timescales. Smaller objects happen more frequently because, like the asteroids game, there are many smaller pieces than there are big ones. We think that the smallest objects, like the size of the one that exploded recently over Russia, maybe a few every 100 years or every few hundred years. That's sort of the level of uncertainty right now. So what do we need to know beyond how many there are and what their orbits are like? We would like to know something about the impact energy, and I promise this is the only equation in the talk, but going back here, basically what you care about is the mass of the object times its velocity. The velocity you get from knowing the orbit. Once you've spotted it and tracked it, you can figure out how fast it's going. But to figure out the mass, you need to know its density and its volume. So really what you need to know is its size. And since the volume scales as the cube of the size, it's pretty important to get the size right. So that's one of the things we'd really like to know, the sizes and the densities. As of today, we know of about 16,000 for which we have orbits. We can say reliably that they do approach within the region of the Earth, and we call them near-Earth objects for that. Sizes, maybe only a couple thousand objects have well-determined sizes at this point. So there's a lot, think of it this way, we know of a lot of objects, but the more you want to know about them, the smaller the number that gets to be, because it's hard to gather this data. When you get down to knowing about the rotational states, how fast they spin, I think it's a few hundred right now that have good rotation states, and I think Sarah, does that sound about right? Okay. And then composition, density, and shape, maybe a few hundred. So the more you want to know, the harder it gets to get that information. It becomes very precious. So NASA has a near-Earth object program that is responsible for studying these objects. Basically now we have, thanks to a lot of dedicated people's efforts, we have actually databases that accept new observations from observers all around the world, automatically compute orbits for the objects and update them as new observations become available, and they also predict impacts in real time. The office also studies ways to potentially deflect something should that ever become necessary, and you can learn more here. Everything is really out in the public eye. All these data sets are available, and you can see what we're paying attention to right now. So this is just a quick summary of some of the workhorses of the observation survey program. So these are survey telescopes that are mostly dedicated to looking for new things. There are 3 on the ground right now, and various other smaller survey efforts that primarily survey. And 1 in space. This is the one that I work on right here, operating at a different set of wavelengths than the ones your eye can see. We are looking for the asteroids with my telescope using heat. So I'll talk more about that in a minute. The worldwide network is very powerful for searching for these objects. It's not just about surveying for them, it's also about tracking them. And this is where, as a colleague of mine likes to say, planetary defense is a team sport. And it really takes the efforts of everybody all around the world to do this well. Because basically when we spot objects, they can be anywhere on the sky practically. So in order to be able to find them reliably again and again and predict where they're going to go, you have to keep gathering more data and tracking the object as it moves across the sky. Right now, there are dozens of countries that contribute observations, and it's a really widespread effort. We really depend on the efforts of both professionals and amateurs alike to learn about the population, including Las Cumbres Observatory Network. This has been an enormously valuable network that is literally headquartered right here in our backyard, and they contribute a huge volume of information, not just about the orbits, but about the composition, the rotational states, and the nature of the populations that we're looking at. So we're really grateful to have LCOGT. Near-Earth object discoveries have really gone up in the last few years. And right here is, let me see here, right here, that was Shoemaker-Levy 9, the comet that crashed into Jupiter. So you can see that really had an effect on what people and astronomy did as a result. That got people's attention in a pretty big way. A lot of efforts were already starting up, and the pioneering efforts of these folks here are why we have these other surveys now. You'll see a few things about this plot, however. This red blob right here represents the very largest objects. Those are the objects large enough to cause global events, like the dinosaur killer. In this more modest size range, however, the curve just keeps going up. And when you look for all of them, which includes the smaller objects, down to the size of, say, the Chelyabinsk impactor, it's going up very steeply. What that means is we've found a large fraction of these guys, but there's way more up here somewhere. That's where the population tops out, and we haven't found all of them yet. So why would we study asteroids with multiple wavelengths other than visible light alone? And this is the work that I've been involved with mostly. Well, it turns out with visible light, what we're sensing is the light bouncing off the surface of the object and reflecting back into the telescope. And that's fine, but as we've said, it's important to know the orbit. We also want to know the size of the object to constrain its potential impact energy. The problem is that if you're just using reflected light to look for them, it can be very hard to tell the difference between an object that is large but very dark and one that's small and much more reflective, lighter colored. So instead, if we look at them with heat-sensitive wavelengths, we are now looking at the heat that's coming off of them, and that's much more directly related to the true size of the object as opposed to what it's made out of and how light or dark the surface is. So if we have good infrared measurements, we can usually nail down the sizes quite well. Considerably better than we can with visible light alone. The other thing, too, is we know that a chunk of the asteroids are really dark, and they're easily missed if you only look for the things that are brightly reflective. So this search using infrared light gives us a representative sample because we can see the bright objects as well as the dark objects roughly equally well. Here's a little bit of an example. I've got 2 coffee mugs here, and to the eye, of course, looking in visible light, they look completely the same. If I use an infrared camera, though, it's immediately obvious the difference in the temperature, which one is hot and which one has ice water in it. We can apply that same technique to looking at the rocks. So I have 2 rocks here, a large dark object and a smaller, brighter one. If I look at them and they're the same size, but one is light and one is dark, if I have a visible light telescope seen from far away, this one looks a lot brighter than that one. But of course, we know that they're the same size. However, if we're looking at them with a heat-sensitive telescope, you can tell the size much more directly, because what you're doing is measuring the temperature of the object. Knowing the distance to the object, we can relate that more directly to its true size. So that's one of the values in looking with an infrared telescope. So this is actually what the telescope looks like that we're using now. Its original name was the Wide Field Infrared Survey Explorer, or WISE. And as telescopes go, it's pretty small. It's about 40 centimeters across. That's the primary mirror, so it's about the size of this podium. So it's not a particularly large telescope. The whole vehicle before launch was about the size of if you took a Miata and stood it up on end, so not terribly large. And it surveys at 4 infrared wavelengths that are quite a bit longer than the wavelengths of light that your eye is sensitive to. So when we put it together, we were not originally planning to really spend a lot of time looking for new asteroids with it. But as it turned out, this was a mission that actually was quite good at finding some of the near-Earth objects. So we called that, because we love acronyms at NASA, Near-Earth Object Wide Field Infrared Survey Explorer, or NEOWISE. And the goal of this was to basically take a survey spacecraft that was really designed to go out and look at the sky in infrared light and try to repurpose it for finding asteroids. So this is what asteroids look like to NEOWISE. They look like a little string of dots. These are individual exposures of the asteroid as it moves across the sky. And you can see that the asteroid is a noticeably different color than the background stars. That's because the asteroid is much cooler than the stars. It's only a few hundred degrees, well, room temperature roughly, but the stars are thousands of degrees. So that heat-sensitive ability helps us to distinguish the objects from the background. Just a few pretty pictures. This is what it looked like when it was all canned up before it got craned up by these little skinny wires on top of the launch vehicle right there. That was really scary. And that's even more scary. That's the really scary part right there. Once you get past that, everything is great. So this is originally what our view of the sky looked like at these wavelengths in infrared light before the WISE mission launched. We had the great virtue of being able to use more modern camera chips than we originally had previously. So this really brought a great benefit to the sensitivity and the resolution of the images. So now these are the type of images that we have available from this mission across the whole sky, thanks to basically 20 or 30 years of investment in producing better, well, essentially better cell phone cameras. Even though the wavelengths are longer, that technology has still directly benefited us. So as a result of operating the telescope for the first roughly 7 or 8 months, this is what we were able to achieve with regards to asteroids. All of these little dots are asteroids that we were able to detect with the spacecraft, and the red and the green are the near-Earth objects that we were able to see. We saw a total of about a few hundred. And the red ones represent new discoveries from our telescope using infrared light. And then the yellow and the blue squares are comets that we saw. So as before, these are the Jovian Trojan clouds ahead and behind of Jupiter, which is over here somewhere. And these are the near-Earth objects sticking around the vicinity of Earth's orbit. What we learned from this study is a couple of things. If you make a plot of the size of the asteroids versus their reflectivity, so more reflective, very dark, what we found is that over a very wide range of sizes, ranging all the way from mountain-sized, or 10 kilometers over here, down to just 100 meters across, there really wasn't much change. In other words, equal numbers of bright and dark objects as a function of size. Previously, studies had found that asteroids got brighter as they got smaller. Well, that's because we were able to show that when you look at them with a reflected light telescope only, you're more sensitive to the things that are bright. So small, dark objects are harder to see. They're still there. That's what this study says. They're right there. But you're just not seeing them if you're only looking with a reflected light telescope. So that was one of the more interesting things about this. The other thing we were able to show is that for a long time there was a suspicion that we had really sort of maxed out on finding all the very large objects. So this is some really good news. The good news is we were able to help confirm that indeed more than 90% of all the really big near-Earth objects have been discovered to date. So that's great. It's great if you're a citizen of planet Earth. I think it's probably bad if you make disaster movies. The good news is we have found a really large fraction now, in fact almost all of the really big stuff that's out there, and we are tracking it, and none of it poses a collisional hazard. So that's the great news. This was the so-called Space Guard goal. I love these names. It sounds very, very dramatic. But this was a goal that was given to NASA by Congress, and we were able to help verify that the goal was achieved. However, there's more work to be done. If you start to break down the objects by size, what you start finding is that while we have found a large fraction of the really big ones, when you get down to the more modest, small-size objects, there are a large fraction that aren't found. And in total, of the objects larger than about 140 meters across, so roughly the size of a football stadium, only about 25% of those have been found to date, and that leaves 75% that remain undiscovered. As we break the objects down by orbit type, it turns out not all orbits are the same among near-Earth objects, and in fact, Sarah Greenstreet, who's here, did some of this work. Basically, objects that have orbits that take them particularly close to the Earth, we call them potentially hazardous asteroids. It doesn't mean they're going to hit the Earth. It just means they have more chances of getting close to the Earth's orbit. We did find with our study that a certain type of those with orbits most similar to Earth, we found that there were more than the models had predicted. But that means we need more study and hopefully a larger sample to help confirm that. Other interesting little tidbits that we turned up, if you remember those Jovian Trojans surrounding Jupiter, it turns out Earth has one too. We have a little friend that shares our orbit around the sun. It is a Trojan asteroid, and it is, at least for a few thousand years, captured by Earth's gravity and is sort of being pulled along as we go around the sun. So that was kind of fun. And like I said, this is what they look like. They look like a string of red dots. And from these dots, though, we can tell the orbits, how far away they are, and something about their size and even what they're made out of a little bit, the reflectivity. So this is asteroid King, named after Dr. Martin Luther King. And his asteroid is about 27 kilometers across with a reflectivity of roughly 30%. Just because it's sort of fun, this is like a magic eye picture. There are actually about 100 asteroids embedded in this image. If you look up close, there are strings of little dots all over it. They're hard to see, but they are there. And this is what the sky looks like at infrared light. We also see in the course of our survey, because we're orbiting the Earth looking up, these things. Does anybody have any idea what these might be? No astronomers, please. Pardon? Nope, think closer in. Satellites. Satellites, yes, these are satellites. These are constellations of, in some cases, and large numbers of satellites passing over our satellite. So they look like raindrops because they're moving so fast that even in a single exposure, they actually streak. That's how fast they're moving. So all good things must come to an end, and our NEOWISE telescope is probably not going to last a whole lot longer, maybe a year, maybe two at most. We're currently scheduled to end the survey at the end of December. The orbit is decaying. It's a natural process. This mission was originally designed to last for 7 months, and it launched in late 2009, December of 2009. So it's been going for a long time, and we're really lucky to have had the extra time with it. Eventually, though, it will end. And like I said, it was never really originally designed for the purpose of finding asteroids and comets. It found in the hundreds, as you can see, from what I described earlier. So what we really want to do, I've been working on another project to basically build a bigger, better, badder version of it that really is designed to go out and find a large fraction of the asteroids that get close to the Earth. We call it NEOCam because we love acronyms so much. So in any case, this is NEOCam. It's the Near Earth Object Camera. This is a future project that I've proposed to NASA. And at this point, we actually have been selected for what's called Extended Phase A study in January of this year. And this is what it looks like. It's basically a telescope with a big old sun shield right here, so it can look over a large volume of the Earth's orbit. And like NEOWISE before it, it will find these little strings of red dots, which are the asteroids and comets. This is what we predict that it will be able to do, because it's optimized for that purpose. So each one of these dots now is a near-Earth object that we expect to see with the telescope. And these are only the larger objects. These only represent the near-Earth objects that are larger than 140 meters. These are the sizes that are thought to be capable of causing severe regional damage. There are lots of objects smaller than that, though, that we will also see, about 15 times more than we could put on the diagram, with sizes down to the size of the Chelyabinsk impactor. So we're working on this right now, and we hope that we'll be able to actually make it a real mission someday. But it's been really fun to work on this. So in summary, the worldwide community of astronomers has done a lot of wonderful work to understand what's out there in our backyard of our own Earth. And there's a lot of great progress that's been made. NASA-funded surveys have found more than 95% of all the known objects to date. So we are your space agency, and we're very proud to do that. The good news is 90% of the dinosaur killer-sized objects have been found. But only about 1% of the objects as large as the 20-meter Chelyabinsk-sized one have been found. So there's lots more work to do, and we're happy to get to do it. Thank you.
So questions for Dr. Mainzer?
What's the size of a comet versus a typical asteroid?
That's a fascinating question because comets come in a wide range of sizes, just like the asteroids. In fact, a colleague of mine has just been doing a study of the relative sizes of comets compared to different types of comets. There are comets that spend a lot of time really, really far away from the Earth and from the sun. And there are those that spend a lot more time near, on the inside of Jupiter's orbit even. And what we're finding is that objects that spend more time close to the sun tend to be smaller. That's because we think that the closer they get to the sun, the more chances they have for the sun to evaporate some of the ice and literally kind of shrink the ice cube, if you will. So comets that spend a lot of time far away, we think tend to be larger, and ones that spend a lot of time tend to be somewhat smaller. That said, they can still be very large, half a kilometer. So asteroids are not actually, in most cases, large enough to have a substantial amount of heat generated from within. Like our planet has a substantial heat source still on the inside. Its core is very, very hot. The largest asteroids, like Ceres and Vesta that you saw, probably have the most residual heat left over inside of them from their formation through the decay of radioactive isotopes. So some of the larger ones still have some amount of that residual heat, but most of the ones that are smaller, sort of the kind of half a kilometer size, their heat is really, in fact all of them, really is dominated by their distance to the sun. So think of it this way, the Earth is room temperature. If you place an asteroid at roughly the same distance from the sun, it's going to be a similar temperature as the Earth, more or less. Put it really far away and it's going to be very cold. So modulo the interior heat thing for the really big guys, most of them, the temperature is strictly determined by how far they are from the sun.
Have you noticed any thermal decline in any of these asteroids due to heating and cooling?
This is a really fun subject. So there's a class of comets, to go back to the comets again, called Sungrazers. And as the name implies, these are comets that stray a little too close to the sun. And in fact, the sun can shred them into pieces or even swallow them up completely. So there was a comet a couple of years back called Ison that was a really kind of fun one to watch because it was going to get about, I think, 3 times the radius of the sun away from the sun's surface. So a really close graze by the sun. And everybody wanted to know exactly this. Would the sun just blow it to bits? Or would the comet have enough structural strength to survive passing that close to the sun's incredible heat? As it turned out, we were able to watch it with NASA observing spacecraft, and it was really kind of dramatic. Basically, this thing came in, and it's blowing off all kinds of gas and dust, and then as it came around the other side, it just sort of fizzled away. So the sun got it. Thank you for asking that question. It's a very important one. So one of the things that has been done in the last 20 or so years is to put in place protocols so that they are there, so there is a procedure. One of the most important things I think that's been accomplished is a computer system and people who run it who take the observations, gather them all up, figure out if the observations we turn in are of a new object or one that we've seen before, and they figure out if it is on a collision course with the Earth. And that all happens now automatically by computer. So that's really important. That was a very important step that happened. Now the question is what to do with the information. So I didn't show this, but there's actually a really nicely laid out protocol for what happens if there is something that's ever found that looks even remotely like it has a substantial probability of colliding with Earth. Basically, NASA notifies the US government and the governments around the world. And in fact, this very week, there's a meeting going on called the Planetary Defense Conference, which sounds like you should have a really cool helmet and a cape if you're at that meeting. But one of the things they're doing is a simulated exercise where they're actually trying to figure out what would happen if there was an asteroid that was found coming toward Earth on a certain timescale. So they're actually doing a simulated exercise to try to figure this out. How would they exactly plan to deflect it, to try to move it out of the way? So yeah, but there's a lot more work to do, certainly. Yes, they're interesting.
The source of water on the Earth, they think came from asteroids, and that has to do with the material, the hybridization.
Yeah, this is a really exciting area of research right now. So the question is, how did Earth get its oceans, and why is this a water planet? That's just a really fascinating question, because if you look throughout the solar system, Earth is really unique. It has a large amount of liquid water on the surface. And one of the major hypotheses for this is that the water could have been brought billions of years ago by either comets or asteroids. Of course, as we're now finding, comets and asteroids are a little closer kin perhaps than we thought. They come from different places in the solar system. But as you mentioned, one of the key determinants for figuring out which might have been the major source is the ratio of heavy hydrogen to lighter hydrogen, so deuterium to regular hydrogen. It's a hard measurement to make. And in a lot of cases, I don't think there have been a huge number of objects. We're not talking about hundreds or thousands of comets where we've been able to look at this ratio. But the ones that have been studied, some of them don't look like such a great match to the signature in the Earth's ocean. So it's perhaps possible that it wasn't so much comets as it was their cousin, the asteroids. So one of the best things we could do is go and get a whole lot more samples and try to see statistically where the better match actually lies. So there's more work to be done there too.
Just a curiosity about the wording. When we talk about an asteroid versus a meteor versus a meteorite, you go take a sample from an asteroid and bring it down to the Earth and set it on your desk as a meteorite?
Oh, that's a very tricky question, actually. So there's an ESA mission called Osiris-Rex that is actually en route to an asteroid right now, and its goal is to bring back a sample, a really precious, roughly softball-sized amount of material. I have no idea. That's great. I'm going to have to ask Dante that question. So that depends on a number of factors, as you can imagine. One of the most important things, though, is having a long time to figure that out. And so that's where the surveys really come in, because our goal is not just to find something when it's a day from impact. We'd like to find things when they're 10 or 20 or 30 years away from impact, or even longer. Because the longer you have, the more options are available, and the less energy it takes. You can imagine, like if you're bowling, I'm a really, really bad bowler. Okay, so if the bowling ball has to go a really long way, I don't have to mess up by very much to make the ball completely miss all of the pins. But if I'm really close to the pins, I would have to twist my wrist a lot more. So what I need to do to be better at bowling is stand right next to the pins. In the same way, we really want to try to find the asteroids many, many decades away from any impact so that we can actually explore a wider range of options. And of course, the more time you have, the better the technology that's available gets as well. However, there is a simple technique that we've already, in some sense, had a test of, which is just deflection. Just take something heavy and run into the object. This is, in fancy terms, called a kinetic impactor. I told you we love jargon. But basically, you hit it with something heavy, going really fast. And this was actually done in 2004. NASA flew a mission called Deep Impact. I don't know if that name came before or after the movie. I'm not really sure. But in any case, Bruce Willis wasn't on the project. However, they did take a big lump of copper, and it was run into a comet. And they were able to watch this incredible amount of material get excavated from the comet's surface. So in its simplest form, one technique is simply to run into the object. If you have enough time, and you need very little energy, like me messing up the bowling ball, very little errors make a big difference in which way it goes. If you have enough time, a kinetic impactor would be a viable approach. You know, I don't think there was. This was a very large comet, and the impactor was really tiny by comparison. But it proved that you could navigate to the comet, and that you could, get in its way and see a big explosion on it.
A few months ago, we had a lecture here from Ed Liu, and you'll forgive me, I can't remember the name of his project. It's not a pronounceable acronym. But I wonder if you're familiar with it, and I wonder how these two projects relate to each other, if they do at all.
So we've actually been working on this particular problem for quite a long time. NEOCam actually was proposed in 2005 to NASA. So we've been working on it for a while. As it turns out, the idea of using an infrared telescope to look for asteroids is not a new one. People have studied it even before my proposal in '05. What happened was the technology was not very mature at the time. The detectors, it was the camera chips. So people have looked at this over time. The difference is that now we've been able to mature the technology, and I think this is where it comes back to your remarks at the beginning, Todd, that the technology is really important. So basically what we've been focusing on over quite a long time now is maturing the detectors that we need to really design a spacecraft that's actually optimized for finding the asteroids. The trick is the temperature. Weirdly enough, infrared detectors need to be operated incredibly cold. So the detectors that are operating on board NEOWISE right now are at about 75 Kelvin, and that's not 75 Fahrenheit. That's about 75 degrees above absolute zero. That's relatively warm for an infrared array at these wavelengths. It's a relatively warm detector. To get at the place where the asteroids are really glowing the brightest, you'd like to even use longer infrared wavelengths than what we're using now. Originally, we had those longer wavelengths on board the WISE spacecraft, but they had to be kept at 8 Kelvin. And so the reason the mission was only originally designed to last for 6 months is that's how long we thought the refrigerant would last. And indeed, it lasted about a little over 7 months. So Ed and his group have gotten interested in the idea of using an infrared telescope to study asteroids more recently than a lot of other folks have been working on this. And I think it's good. But, you know, the trick is publicly funded science is important. And relying solely upon private donors to carry out big infrastructure projects like this is hard. So, like the Weather Service, we rely on our government to take on these big and challenging tasks. We've been very lucky that NASA has been funding our technology development, and we finally now have the camera chips that we need. In the last 5 years, we've finally been able to make detectors that now operate, instead of at 8 Kelvin, at about 35 to 40, which still sounds very cold, but to an infrared detector person, that's actually a warm day. So these are chips that don't need refrigerant. They will last for a decade sitting in space and just continuing to operate. So we wish them well, and we hope that they support continued efforts to find asteroids, because that's what we all want to do.
Okay, let's thank Dr. Mainzer again.
Thank you.